Hello again, this is Professor Roman. Welcome back to my lecture series entitled Transition to Advanced Mathematics. Let's continue our discussion of mathematical induction. You might recall that back in chapter 4, we proved, in Theorem 419 specifically, that x minus r divides x to the n minus r to the n for any n bigger than or equal to 1, and this took us a bit of effort. I mentioned at the time that perhaps the simplest way to prove this is by induction, so let's take a look at that now. To prove the proposition P of n that x minus y divides x to the n minus y to the n, we can proceed by induction on n. The basis step is clear. P of 1 certainly holds. And if P of n holds, then all we have to do is write x to the n plus 1 minus y to the n plus 1. We have to extract x to the n minus y to the n. So we can use the inductive hypothesis. And that can be done by writing this formula. Then the inductive hypothesis tells us that x minus y divides this term, but x minus y obviously divides that term, so x minus y divides this side. In other words, P of n plus 1 is true, and the proof is complete. So it's a very simple, short proof. Key is recognizing this formula. Let's look at a geometric example of proof by induction. As shown in this figure, if we draw several straight lines in the plane, then the plane will be divided into distinct regions. And I'll refer to these regions as countries and the entire figure as a map. Now we'd like to color the countries of this map with two colors, and I'll use gray and white, in such a way that no two countries that share a common border, and by that I mean a line segment, not just a point, have different colors. This is done for this map here, M prime. You can see that each country that is colored white or gray, and that countries that share a common border are different colors. This point here is not a border, so these two do not share a common border. Now, we'd like to prove that any map can be colored. Any map like this can be colored with two colors, so that countries that share a common border are a different color. So let's let P of n be that statement that any n-line map has what I'll call a proper coloring, meaning that the countries that share a common border have a different color. And I'll refer to a country as being properly colored if its neighboring countries have a different color. Now, here's how we handle this. P of 1 is certainly true, because if there's only one line, there's only two countries. Suppose P of n is true, so any map with n lines can be properly colored. And consider this map here, which has m plus 1 lines, n plus 1 lines. So I want to show that I can still color this map, assuming I can color any map with one fewer line. So to get a map with only n lines, I take one of the lines and take it out. So this line L, if I remove it, I then get this map which has n lines and can therefore be colored properly, as I have done here. The question is, if you restore the line that's missing, you've loused up the proper coloring. You can see here there are two countries sharing a common border, but they're both gray. So what to do? Well, here's the key idea. Suppose that we reverse the colors of all the countries that lie above the line L. If L is vertical, then we have to choose either right or left. It doesn't matter. I've done that here. So below the line L, everything is the same, but above the line, I've swapped the colors. What was white is now gray. What was gray is now white. This, as it turns out, is a proper coloring of the n+1 line maps, and so P of n+1 is true. To see this as a proper coloring, the best thing to do is focus on the borders, not the countries. There are going to be some borders may be part of the line L. You can see 1, 2, 3, 4 borders here are part of the line L. Other borders like B1 here and B2 are not part of L. Among the borders that are not part of L, there are two types, the ones that don't touch L and the ones that do, and those borders get cut into two separate borders by L. Now you have to go through and think about these different types of borders. For example, this border B1 was completely contained above the line. So the countries on opposite sides of B1 that used to be gray above and white below, I've swapped the two. But the point is, they're still different. This border B2 that cuts through L has a piece above and a piece below. The piece below, there's been no change in the country's colors, and so they're still opposite colors. The piece above used to be opposite colored on both sides, but still is, it's just they're reversed. And finally, you need to take a look at borders that are part of the line L. Well, these borders cut countries into two parts, and they are the same color, but we swap everything above the line, which means they're now opposite colors. So you might want to think some more about that. But this argument does show that if a line if a map with n lines can be properly colored, so can a map with n+1 lines. And so that's the inductive step, and shows that all maps with n lines can be properly colored. Here's one more example of induction. There's a famous game or puzzle called the Towers of Hanoi puzzle. And it goes like this. You start with a platform with 3 vertical pegs. And on the first peg sit a bunch of concentric discs. The discs have a hole in them so they'll fit over the peg. The object of the game is to get all these discs from the first peg to the third peg. But you have to follow the rules of the game. Only one disc can be moved at a time, and a disk can be placed only on top of a larger disk. And the question is, can you complete the puzzle? Can you move the disks? Well, if the number would do but this by will prove that it's possible by induction on the number of disks, which is n. If n is one disk, no problem. So suppose that you can, in fact, move n disks from the first peg to the third peg following the rules of the game. It's pretty clear based on symmetry grounds then that you can move the stack of disks from any peg to any other peg. There's a symmetry in the three pegs. It might be better if you could look at the game from above. If you put the three pegs in that orientation, you can see that they're all essentially the same orientation. It doesn't matter where one is. If you can move all the disks from one peg to another peg according to the rules of the game, you can do it between any two pegs. So to prove that you can, if you can move n disks, you can move n plus 1 disks, all legally done, then here's how that goes. This is the starting position. Leave the bottom disk alone. You have n disks which you can move to the second peg legally, following the rules of the game. Then you can move the largest disk from this peg to this peg, the third peg. Then you can use the inductive hypothesis a second time to move the n disks over here, because this large disk doesn't come into play. You can pretend it's not there while you're moving these disks, because this is the largest disk, so you won't violate the rules of the game. Okay. So if you can move n disks, you can move n plus 1 disks, and therefore, by induction, you can move any number of disks. So the Towers of Hanoi puzzle can always be solved no matter how many disks you have. I think the original version, there were 8 disks in the game, but now we know you can move any number of disks legally. There is another form of mathematical induction that I want to talk about now. It is referred to as strong mathematical induction, and so the version we've been discussing so far would be called weak mathematical induction. The strong form looks like this. M is an integer, that's our starting point for the induction. For each integer n bigger than or equal to m, let P of n be a proposition. Then if the following hold, the basis step P of m is true. And for the inductive step, we have something a little different. If the conjunction of P of m through P of n holds, then P of n plus 1 holds. If we can prove this, then P of n holds for all n bigger than or equal to m. So it's the inductive hypothesis here, what we are allowed to assume in order to prove P of n plus 1, that's much stronger. Hence the term strong induction. We got a lot more ammunition here, you might say, because we get to assume all of these propositions are true, all the way from P of m all the way up to P of n. Whereas in the weak form, we're only allowed to assume the previous proposition P of n in order to deduce the next proposition. Even though it does seem like the strong form is a stronger property, it's not really. It turns out, and we'll talk about this later on, that both forms of induction either form can be used to prove the other form. This is a little bit different use of the term strong and weak than we have had before. For an example, when we talked about disjointness of sets, let's say 3 or more sets, we talked also about pairwise disjointness, and we observed that pairwise disjointness implies disjointness, but not the other way around. The converse fails. There are disjoint families of 3 sets that are not pairwise disjoint. So here, in that case, we have a situation where pairwise disjointness is strictly stronger than disjointness. It's harder to be pairwise disjoint than it is to be just disjoint, strictly harder. The terms strong and weak, as they're used here for induction, refer only to the inductive hypothesis, not to the overall strength of induction. So after we've shown that either form of induction implies the other, we can conclude that neither one is stronger than the other. So the strong form of induction is not stronger than the weak form as a proof technique. It's only the hypothesis, the inductive hypothesis, that's stronger. So these really are 2 different but equivalent versions of induction. It should be pretty clear, actually, that any result that can be proved using the weak form of induction can also be proved using the strong form. If we can prove that P of n implies P of n plus 1, then of course we know immediately that this conditional is also true. We just don't need the other assumptions. All we need is P of n. The other direction is a little more subtle, and we'll get to that. So let's look at an example. The strong induction is a technique that, while not any stronger than weak induction, does sometimes work much better than weak induction. And I'll give you a couple of examples where it would be difficult to use weak induction, but it would be very easy to use strong induction. The first example is the fundamental theorem of arithmetic. This is obviously an important property. It wouldn't be called the fundamental theorem of arithmetic. And it says that any integer n bigger than or equal to 2 can be factored into a product of 1 or more prime numbers. If n is prime, then it's a product of 1 prime factor. This is a little bit more convenient language than having to say every integer greater than or equal to 2 is either prime or can be factored into a product of 2 or more prime numbers. This is just a little bit easier to say. Amounts to the same thing. In addition, the factorization is unique if we don't count the order of the factors. So unique up to the order of the factors. To prove that the existence part, this is an existence and uniqueness theorem. The existence of a prime factorization and its uniqueness. So we've got 2 things to prove. As far as the existence part is concerned, what we need to prove if we were going to use the weak form of induction is that if n is a product of primes, so is n plus 1. That's not so clear how you would do that. What we can say is that if n plus 1 is not prime, then it can be factored into a product AB, where A and B are bigger than or equal to 2, but less than or equal to n minus 1. In fact, if since, for example, A is bigger than or equal to 2, B has to be less than or equal to n, but in fact it can't be n because 2n is already bigger than n plus 1. So A and B have to be less than or equal to n minus 1. And you can see right now this is going to be of no use for weak induction, because weak induction, the only thing we're allowed to assume is that n can be factored into a product of primes. Neither one of these is n, so we're kind of stuck. But this is tailor-made for the strong form of induction, because there we get to assume P of 2 through P of n are true, which means P of A is true and P of B is true. So both A and B are a product of primes, like this, for example, and so their product, which is n plus 1, is a product of primes. And so P of n plus 1 is true, and we've completed the strong induction. So this is something definitely to go over until it's crystal clear that the weak form of induction, while it may work, is going to be much more trouble than the strong form. Now, since this is an important theorem, and since part of this course is studying proof techniques, we should probably look at the proof of the uniqueness part. And it's not very difficult, and that will complete the proof of the fundamental theorem of arithmetic. So as to the uniqueness part, suppose that we have an integer n bigger than or equal to 2, and it has two prime factorizations. We want to show that the factors on both sides are the same, except possibly for order. Well, the first thing we can do is cancel any like factors on both sides. So let's assume that's been done. It will result in an equation where we have a product of some of these primes equals a product of some of these primes. Now, it would be quite awkward to have to double subscript and explain which ones are canceled and which aren't. So it's a common ploy to simply say, for convenience, after canceling like primes on both sides, we re-index, if necessary, change the indices of the remaining primes P and the remaining primes Q, so we can write P1, the product of P1 through PS equals the product of Q1 through QT. This is a very common thing to do, is re-indexing if necessary, just to clean things up. So none of the primes on the left side here, none of the p sub i's, are equal to any of the q sub i's. They're all distinct on both sides. Some of the p sub i's may be equal to each other. Usually that happens. Some of the q's may be equal to each other, but the p's and the q's are different. Now, there are three possibilities here, depending upon whether one or both of these sides are equal to 1. It's possible that if you look back here, if we do the cancellation, all of the q's get canceled against some of the p's. So this side would become 1. That would be indicated by setting t equal to 0 here, but we don't have to worry about that. A similar issue could occur on the left side. So we have three cases to consider. First case would be neither side of this is equal to 1, so there are primes on both sides. If neither side is equal to 1, then we can scan through the P's and scan through the Q's and find the largest number on both. Look at both sides. Pick out the largest prime. Let's call that M. This value can only appear on one side of the equation, because if it appeared on both sides, we didn't finish the canceling. And it may appear more than once on one side. But in any case, we can assume by the symmetry of the P's and the Q's that it's one of the P's that takes on this maximum value. Okay. And therefore none of the Q's do. We can also, again, re-index if necessary and assume that P1 takes that maximum value, M. Well then, a corollary from chapter 4, 4.51, tells us that since P1 divides the product of the Q's, it must divide one of the primes, Qi. But that's not possible, because P1 is bigger than all of the Q's. P1 is the largest value among all the primes. And none of the Q's take on that value, so they're all smaller. So this is a contradiction, and it tells us that in the reduction, after cancellation, one side or the other, at least one side, must be equal to 1. All the primes are canceled. But if only one side of the equation is equal to 1, the other side still has some primes, and we're in a situation where a product of primes is equal to 1, which also is not possible. The only possibility left is that the cancellation has produced the equation 1 equals 1. All the primes got canceled on both sides. But that tells us that the primes on both sides matched up perfectly. And so all the P's are Q's and all the Q's are P's. The only possible difference between these two is the order of the factors. And that proves the uniqueness. So we can now officially state the fundamental theorem of arithmetic, which we have just proved. This is an important result, and you should pause, I think, to reflect a little bit on the progress you've made so far in this course. If I told you to prove the fundamental theorem of arithmetic on the first day, you might have had significant problems doing that. Now you have developed the techniques to enable you to actually prove a significant result in mathematics. Here's another example that's not at all significant, but it's kind of fun. And you'll see this example formed in different ways. It's quite a common example. The post office hires you as a consultant because you have taken this Transition to Advanced Mathematics course. That makes you very desirable because you now know how to think. Your first task on the job is the following. The post office wants to print only 3-cent and 5-cent stamps. But before doing so, they need to know exactly which amounts of postage can be formed using only stamps of those two denominations. So just as an example, after a teensy-weensy bit of inflation, the new price for first-class shipping across the country is $5,746.97. So the post office wants to know, can I can this amount of postage be formed using only 3-cent and 5-cent stamps? We can put that more algebraically. Is there a solution in non-negative integers x and y to this equation 3x plus 5y equals this number of pennies? More generally, what your boss wants to know is, given for which values of n, which positive integers, does this equation have a solution in non-negative integers x and y? You can't have a negative number of stamps on an envelope, so x and y have to be non-negative. This may seem like an algebraic problem that is not amenable to induction, but it is. And the reason is that if we can form p minus 3 cents worth of postage, then we can form p cents postage just by throwing in another 3-cent stamp. Now it begins to sound a little bit like an inductive type of argument. Well, to apply the weak form of induction, we need to show that if we can form n cents of postage using only 3 and 5 cent stamps, then we can also form n plus 1 cents of postage. And that sounds a bit awkward, because obviously n and n plus 1 don't differ by any multiples of 3 or 5 or 5 minus 3, which is 2. So it might be a little unclear how to proceed. But the strong form, again, is perfect for this situation because it'll allow us to step back 3 by 3 cents rather than 1 cent. So the first thing to do is look at some small examples until we can form postage for 3 successive values. So I created this table. You can't form 1 cent, 2 cent, or 2 cent 1 cent or 2 cent postage using 3 and 5 cent stamps, obviously. You can do 3 cents. You can't do 4 cents. You can do 5. You can do 6, 2 3-cent stamps. You can't do 7, but you can do 8, 9, and 10. So there is our 3 successive postage values that are amenable to construction using 3 and 5 cent stamps. Now, so we'll let P of n be the proposition that n cents postage can be obtained by combining 3 and 5 cent stamps. We can come up with an intuitive argument that then all postages from 8 cents on can be formed with 3 and 5 cent stamps by reasoning as follows. We know P of 8, P of 9, and P of 10 hold. And since we can always add 3-cent stamps, as many as we need, any amount of postage of the form 8 plus a multiple of 3, or 9 plus a multiple of 3, or 10 plus a multiple of 3 are obtainable. So these 3 propositions are true for all k bigger than or equal to 0. But every integer n bigger than or equal to 8 will have one of these 3 forms. One way to see that is to note that any integer bigger than or equal to 0 can be written this way using the division algorithm. A multiple of 3 plus a remainder, which is 0, 1, or 2. All we need to do is add 8 to both sides. So 8 plus m is 3q, a multiple of 3, plus r plus 8, where now r plus 8 is either 8, 9, or 10. So every integer m plus 8, and m is bigger than or equal to 0, so this represents all possible integers bigger than or equal to 8 has one of these forms. So that's an argument that says we can form postage of any size starting at 8. It's a little bit informal. It's a disguised form of a formal inductive proof. It's actually the application of induction, even though it doesn't quite sound like it. If we want to fit the precise pattern given in the theorem for strong induction, we can do that as follows. First of all, we know that P of 8 holds, and that's our basis step. Then we have to show that if P of 8 through P of n hold, then P of n plus 1 holds. N is bigger than or equal to 8. So we get to assume P of 8 through P of n holds to show that P of n plus 1 holds. Now, we have to take two cases, just separate them. If n is 8, then n plus 1 is 9. We already have shown that P of 9 holds. If n is 9, then n plus 1 is 10, and we've already shown that P of 10 holds. It's in the table I gave you. So we can now assume that n is at least 10. Now you see when we back up 3, we'll be in the right range. So to show that P of n plus 1 holds, just note that n plus 1 minus 3 is n minus 2, and because n is now bigger than or equal to 10, n minus 2 is bigger than or equal to 8. And that's what we need. Because that means that P of n, that means that n plus 1 minus 3, n minus 2, in other words, is one of these numbers. It's bigger than or equal to 8, and of course it's less than n. So it falls in this range where we are allowed to assume the proposition is true. So P of n minus 2 holds. Then we kick in another 3-cent stamp showing that P of n plus 1 also holds. So all amounts of postage are possible using 3 and 5-cent stamps, except those few small numbers 1, 2, 4, and 7. Except for those 4 values of postage, we can form any amount of postage using 3 and 5-cent stamps. So you've earned your salary. This one is worth looking over carefully because there's a little wrinkle there in having to deal with a couple of cases separately. So you might want to go back and say, well, what if I didn't separate out n equals 8 and n equals 9? Would the rest of the argument still work? Well, there is another way to express the principles of mathematical induction. This is called the well-ordering principle, sometimes abbreviated WOP, and it states that any non-empty set of natural numbers has a smallest element. I guess that should seem pretty obvious, and you could reason as follows. If S was a non-empty set of natural numbers, S contains some natural number, call it n. There's only a finite number of values between 0 and n. We just check them to see which start at 0 and ask yourself, is that in the set? If you say no, then is 1 in the set, and so on. You'll find the smallest element. So this is about as obvious a statement as you can have, but my argument, the one I just gave you, is totally informal. Okay. We've seen that weak induction implies strong induction, that if we can prove something using weak induction, if weak induction holds, then strong induction holds. We're going to show how strong induction can be used to prove the well-ordering principle, and then how the well-ordering principle can be used to prove weak induction. So we have then shown that the 3 principles, strong induction, weak induction, well-ordering principle, are logically equivalent. And beyond logically equivalent, each one implies the other directly, or more or less directly. Okay. You know, to say that 2 statements are logically equivalent, this is something a bit subtle. Perhaps I should have mentioned it sooner. If you have 2 statements, 1 plus 1 equals 2, for example, and say the distributive law of union and intersection, those are both true. Therefore, if one is true, so is the other. If one is false, so is the other. They're true at the same time because they're always true. Therefore, by definition, they're logically equivalent. But they're not connected. So that the statement that they're logically equivalent is really not very useful. What we're talking about here is that one of these statements actually can be used to pretty much directly imply another. And that is the meaning here of logically equivalent. There's the sense in which we're using the term logically equivalent. So maybe it's even better not to say logically equivalent, just simply to say that each one can be used to imply or to prove the other. All right, let's take a look at the theorem and the proof. The principle of weak induction implies the principle of strong induction. The principle of strong induction implies the well-ordering principle, and the well-ordering principle implies the principle of weak induction. Hence, these 3 principles are logically equivalent and therefore valid because weak induction is valid. We proved that. We justified weak induction using the formal definition of the natural numbers. So we've already taken care of weak induction implies strong induction. That's almost trivial because if you have P of n implies P of n plus 1, then you certainly have P of m through P of n implies P of n plus 1. As for the second part, how strong induction applies the well-ordering principle, here's how we might prove that. Start by letting n sub k be the set of natural numbers from 0 to k. Now suppose, for the purposes of contradiction, that there is a non-empty subset S of the natural numbers that doesn't have a smallest element. We want to examine the relationship between S and these sets n sub k, of which there are infinitely many. Since S has no smallest member, by assumption, 0 is not in S, which means that S intersect n naught is empty. N naught is just the set containing 0. Also, since 0 is not in S, and S has no smallest element. 1 is not in S, and so S intersect N1 is trivial, empty. Well, it's not a whole lot of pattern, but there's a little bit here. It sounds like maybe S intersect NK is empty for all K. If that were true, we'd have a contradiction, because S then would have to be the empty set, which it's not. Okay. Remember, S is a set of natural numbers, so if it doesn't intersect any of these sets, it doesn't have anything in it. Well, now we are talking about proving an infinite number of propositions. P sub k is the proposition that S intersect NK is empty. Time for induction. P of 0 is true. We've already done that. We even did P of 1, but we don't need that. So in the strong form of induction, we can suppose that P of 0 through P of n are true. And we need to show that P of n plus 1 is true, that the intersection of S and n sub little n plus 1 is empty. Well, if this failed to hold, if P of n plus 1 failed to hold, then that would mean that S intersect capital N of n plus 1 is not empty. So because P of n is true, none of these integers belong to S. And therefore, if this is non-empty, it's because n plus 1 is in both of these. And so n plus 1 has to be in S. But then this tells us that n plus 1 is the smallest element in S. Contradiction. So P of n plus 1 has to be true. And so P of n is true for all n. So that means that S intersects all of these sets trivially. The intersection's empty, which means S is empty, and we still have a contradiction, so the well-ordering principle has to hold. We've done a couple of contradictions in here, so it's worth going through this proof and seeing in the two cases where we contradicted, what are we contradicting? Okay. Also, you might ask yourself, did I need strong induction, or was weak induction sufficient here to handle this? Okay. So go back and take a look and say, did I need all these hypotheses here, that all these are true or not? And I'm going to leave that for you to think about. Okay. Part 3, we assume the well-ordering principle, and we want to show that weak induction must hold. So suppose that P of n is a sequence of propositions for n bigger than or equal to our starting point m, that P of m holds, and also that we have been able to show that P of n implies P of n plus 1. We want to show that P of n holds for all n bigger than or equal to m. Suppose to the contrary that that wasn't true, then the set of all integers k bigger than or equal to m, for which P of k fails to hold, is non-empty. And so we had to maneuver this so that we could apply the well-ordering principle. And that will tell us that S has the smallest element, say little s. That's, of course, greater than m because P of m is true. So m does not belong to the set S. Well, if little s is the smallest member of capital S, the failed integers, s minus 1 didn't fail. P of s minus 1 is true, but P of s is false, and that contradicts this. And so we've assumed that not all the P of n's are true. We have a contradiction. Therefore, all the P of n's are true. And so induction holds. Weak induction holds. A concept that's closely related to proof by induction is something called definition by induction. This type of definition is frequently used in mathematics and even more so in computer science to define the elements of a particular set. So as a very simple example, we can define the even integers in the following way. The set E of non-negative even integers is defined by the following conditions. 0 is in E. If n is in E, then so is n plus 2. If we stop there, we would know that the set E contains 0, and therefore it contains 2, and therefore it contains 4, and 6, and 8, and so on. But unfortunately, that's not a complete definition because it doesn't say what else it might contain. We have to find a way to limit the contents of the set E to just those things that you get by starting from 0 and adding 2 any number of times. So there has to be a third clause to this definition. Nothing is in E unless it can be obtained by a finite number of applications of statements 1 and 2. You're only going to use statement 1 once, so it's really statement 2 that's going to be applied a finite number of times. So this definition tells us exactly how to identify the elements of E. And while the non-negative integers, of course, can be defined in simpler ways, they're simply the set of all natural numbers that are divisible by 2. There are cases where the inductive definition approach is the simplest way to define certain sets. Here's the formal definition of an inductive definition. An inductive definition for a set S consists of the following 3 parts: a basis clause, which tells us that certain specific elements belong to the set S. So it may be more than one element. An inductive clause, which tells us how to use the elements that we already know are in the set S to get additional elements of S. And then a limiting clause, which tells us that the only elements that are in S are the elements that can be obtained from a finite number of applications of the first 2 statements. As another example of an inductive definition, here is a somewhat reformulated definition of a well-formed formula from the propositional logic, which goes way back to chapter 1. A well-formed formula, abbreviated WFF, is any of the following. Any variable is a well-formed formula. So remember that the proposition, the language of the propositional calculus includes variables. The inductive clause says that if W and V are well-formed formulas, then so are each of the following. And you may recall why we required the parentheses on these, so that we could build more complicated formulas unambiguously. And then a limiting clause, which says that an expression omega is a well-formed formula if and only if it can be obtained by applying a finite number of constructions of the form 2, starting with one or more variables. It's a slight variation on language, but that gets the point across. Here's another important example of an inductive definition. In fact, this is a concept we haven't discussed, but is also important in mathematics and computer science. If A is a non-empty set, then a word over A is just a string consisting of 0 or more elements of A, with repetitions allowed. In this context, the set A is called the alphabet. So, for example, if the alphabet is 1, 2, AX, then these are words over that alphabet. Just strings of symbols taken from the alphabet. The length of a word is the number of characters in the word, so the length of AX12 is 4. There's also something called the empty word, which is the unique word that has length 0. It has no symbols in it. The empty word is often denoted by the Greek letter epsilon. And the set A star is the set of all words over the alphabet A. And I think I forgot to say that, actually, so I'm going to stick that in here. When you, in the book, it should be in the book by the time you get the book. In any case, A star is the set of all words over the alphabet A. And there is an algebraic operation on A star known as juxtaposition or concatenation. And all you do, if I denote it by a star, all you do is set two words. So this is A1C star 2C3. You just combine the words in order. You juxtapose them. The empty word does nothing. When you concatenate by the empty word, it doesn't do anything. Here is an inductive definition of the term word. Let A be a non-empty set, then define the set A star of all words over A inductively as follows. The basis clause, the empty word is an A star. Inductive clause, if W is in A star, then so are AW and WA for any little a in the alphabet, capital A. Limiting clause, nothing is an A star unless it can be obtained by a finite number of applications of statement 1 and 2. Binary words are particularly important in computer science, and the definition here mimics this one, but the set A now is just 0 and 1, so it's often denoted by capital sigma. So the binary words over sigma are defined inductively, this way. The empty words in sigma star, if W is a word over sigma, you say a word over sigma or a word in sigma star, then so are 0W, W0, 1W, W1, and then you have the usual limiting clause. Another example, an arithmetic expression, intuitively speaking, is an expression formed by adding, subtracting, multiplying, and dividing a finite number of real numbers. Parentheses are generally needed to avoid ambiguity. So you would need parentheses. So this would convey the intended meaning that you add first and then you subtract. And never hurts to include more parentheses than you need, as long as they're legally placed. Even though, so in this case, there are some here that aren't required. But the formal definition of an arithmetic expression would be a little difficult to give directly without an inductive kind of definition, because inductive definitions build, and that's a very useful idea. So the set S of all arithmetic expressions over the real numbers is defined inductively as follows. If R is a real number, then R is in S. So in other words, every real number is an arithmetic expression all by itself. If X and Y are arithmetic expressions, then so are plus X, minus X, positive X, negative X, X plus Y, X minus Y, X times Y, X divided by Y, provided Y is not 0. And again with parentheses around them to avoid any potential ambiguities that would arise when you apply a finite number of these building rules. And here is the usual limiting clause. So this is a really good example of an inductive definition, because it might be something worth thinking about, but it's not clear immediately to me how you would define an arithmetic expression without some form of inductive operation, you know. Okay, that concludes our discussion of mathematical induction.